Hi, this is Dr. A with a video on oxygen transport and exchange as part of our Clean Chem acid-base review. So tissue oxygenation is really what breathing is all about. It's about getting oxygen to the tissues so that your metabolic reactions can happen. So there are a lot of different things that have to happen in order for you to get adequate tissue oxygenation. So first of all, you got to have enough oxygen to breathe. So that's evident, but for example, if you're like way high on a mountaintop, you may not have enough oxygen, the oxygen's thinner. Or if you're locked into something, a box or something where you're not getting enough oxygen. That's kind of scary to think of, but all right, available atmospheric oxygen, or if you're out in space, you won't have enough oxygen, right? The second one is adequate ventilation. So this is being able to breathe air into your lungs and of course then back out. So what can mess with that would be if you were choking, if you had anything, lodged in there, tumors and stuff could mess with ventilation, but also lots of mucus and infection and stuff like that. Those can interfere with the air moving in and out of the lungs. And then you have the gas exchange between the lungs and the arterial blood. So the gas has to be able to cross over from the alveoli and across the respiratory membrane and go into the capillaries there around the lungs. And things that damage that respiratory membrane can cause it. So if there's scarring or loss of surface area, like there is an emphysema, or if there's like pulmonary edema and stuff like that, those things can interfere with the gas exchange. And then, of course, once the oxygen crosses over into the arterial blood, it has to be able to load onto hemoglobin. And so, for example, something that might interfere with that would be carboxyhemoglobin, or because the carbon dioxide is bound where the oxygen is supposed to bind on hemoglobin, and then the oxygen cannot load. Then you have to have adequate hemoglobin. You have to have enough hemoglobin. So, for example, if somebody's anemic and they don't have enough red cells or enough hemoglobin, then they will not be transporting as much oxygen and therefore not get adequate tissue oxygenation. And then adequate transport. So the heart has to be beating and the blood has to be flowing. And things that could mess with that would be, blood clots, for example, in certain areas could mess with tissue oxygenation to certain tissues. And the heart not beating obviously would be a problem too. And then the release of the oxygen into the tissues. There are several factors that can affect that. Some of them have to do with the pressures of the gases and all of that. So the oxygen has to be able to let go of the hemoglobin and cross over into the tissues. Some of the factors, the most common one that influence the amount of oxygen that moves through the alveoli and into blood and then into tissue would be the destruction of the alveoli, again from scarring, or from emphysema and the other types of damage to the lungs. Pulmonary edema, which is fluid accumulation in and around the lungs, which then will mess with the gas exchange. Any airway blockage, so anything that messes with ventilation, the air moving. An inadequate blood supply, right? So the low hemoglobin, stuff like that, anemia, traumatic blood loss, all of that. And of course, the diffusion of the gases, so things that affect the diffusion of CO2 and O2 across the different membranes. So oxygen is necessary for life. We need it to make ATP, and we need ATP to drive all the chemical reactions. As long as we get that oxygen and we get from that ATP and we can drive our chemical reactions, then we have life and health and everything is good. Oxygen is transported by hemoglobin. Each hemoglobin molecule can transport 4 molecules of oxygen because it has 4 globin chains, and each globin chain has 1 heme molecule, and 1 heme molecule will carry 1 molecule of oxygen. Blood hemoglobin will exist in 1 of 4 conditions. You have oxyhemoglobin, which is hemoglobin with oxygen reversibly bound to it. You have deoxyhemoglobin, which is hemoglobin that is simply not bound to oxygen, but could bound to oxygen. So it's also known as reduced hemoglobin. Then you have carboxyhemoglobin, which is hemoglobin that is bound to carbon monoxide. This is commonly seen in smokers, and it is also, of course, commonly seen in anybody that's had smoke inhalation, been a house fire, or that kind of stuff. Car exhaust has carbon monoxide also. Methemoglobin is a hemoglobin that cannot bind oxygen because the iron is in an oxidized state rather than in a reduced state. Now, let's talk a little bit about oxygen saturation. So the ratio of oxygen saturation is defined as the ratio of oxygen that is bound to hemoglobin as compared with the total amount of hemoglobin capable of binding oxygen. It's usually expressed as a percentage. So an average person, if you're healthy and well, your oxygen saturation should usually be somewhere definitely above 95, but I would expect you to be like 97, 98%, 96%, somewhere around there. You should be pretty good there. It is usually measured by a carboxymeter in the blood gas analyzer. That's the portion there that measures that. And the carboxymeter measures absorption of light at different wavelengths and of hemoglobin. And so it can distinguish between oxyhemoglobin and other types of hemoglobin because they have different colors. And so it can calculate the percent saturation. So just to give you an idea of the ranges of colors. So these would be typical of arterial blood. This is like nice, bright, kind of cherry red, and then this darker, like more purpley red would be more indicative of a venous blood or very low oxygen saturation. The hemoglobins that affect oxygen saturation can include carboxyhemoglobin, so that's with carbon monoxide bound to it, methemoglobin, which is with reduced, when self-hemoglobin, that one happens a lot of times with exposure to sulfur drugs and stuff, and then sign methemoglobin, which is like a blue. And all of these hemoglobins do not allow oxygen to bind to the hemoglobin, so they interfere with hemoglobin binding to oxygen. So, and oxygen saturation less than 95% is indicative of a decreased ability to transport oxygen. So if you're less than 95%, then there's going to be some concerns. And other factors that affect oxygen transport can include the partial pressure of O2 and the diffusion of oxygen across the alveolar membrane. So for example, again, emphysema and pulmonary edema are two conditions that can affect this diffusion because there's either loss of surface area or there's a problem with the fluid interfering with the gas exchange and stuff. So different ways to assess a patient's oxygen status. The most commonly used is oxygen saturation, and that is the percentage of O2 bound to hemoglobin compared to with the total amount of hemoglobin capable of binding to O2. So usually, again, the O2 sat is a percentage, and you would expect normal patients to have above 95% oxygen saturation. So there are trends in oxygen saturation that can be monitored, so you can assess it by transcutaneous pulse oximetry, and then you can see how they're moving, and it can be recorded and all of that. Fractional oxyhemoglobin, also measured with a carboxymeter, it's the ratio of the concentration of oxyhemoglobin to that of total hemoglobin, but this takes into account the effects of abnormal hemoglobins such as carboxyhemoglobin, methemoglobin, self-hemoglobin, etc. So if these guys are present, then your fractional oxyhemoglobin may be decreased while your oxygen saturation is actually normal. And you can also assess oxygen contents. That's just the total O2 in blood, and it's going to look at the O2 that's bound to hemoglobin and the amount that's dissolved in plasma. And then last, let's talk about hemoglobin-oxygen dissociation. So hemoglobin has to be able to pick up oxygen and then let go of oxygen at the appropriate times. So where you wanted to let go of oxygen is at the tissues so that it can cross over into the cells and be used to create ATP. So normally oxygen dissociates from adult hemoglobin, which is A1 hemoglobin, in a characteristic fashion. It's like an S-shaped curve, which I'm going to show you here in a second. The shape of that oxygen dissociation curve and the affinity of hemoglobin for oxygen, which is how much it wants to hold on or can bind the oxygen, they are affected by hydrogen ion activity and therefore pH, the CO2 levels, the body temperature, and 2,3-DPG levels. And I found this graphic here that kind of illustrates it. It has most of the factors on here. But so in dark, you have the normal oxygen dissociation curve. And then we talk about left shift and right shift. So if the curve shifts to the left, there's a higher affinity of the hemoglobin for the oxygen. This happens in conditions of lower CO2, higher pH, and lower temperature. And if you see, it takes a lower pressure, for example, of oxygen at 20 millimeters of mercury, you can achieve a 60% saturation of hemoglobin with oxygen. Whereas if the curve shifts to the right here, you have a reduced oxygen hemoglobin affinity. These are conditions usually of higher CO2, lower pH, and higher temperature. Higher CO2, for example, would be at the tissue level. And it takes a higher amount of the pressure of oxygen for it to bind in onto the hemoglobin. So if you wanted to achieve the 60%, you would have to have a partial pressure of 40, so 20 more than was earlier to achieve the same amount of percentage here. So you can see at 60% at with the low, if there's a lower CO2, higher pH, and lower temperature, it only takes 20 millimeters of mercury to achieve 60%. But if you have a higher CO2, lower pH, and higher temperature, it's going to take about 40 millimeters of mercury to reach 60% saturation of oxygen on hemoglobin. And so that is a quick review of the oxygen hemoglobin dissociation curve, and that is it. Thank you so much.